Okay, so for this discussion, we're going to go over the functions of the respiratory system. So that is the packet that you should have with you right now. We pair the respiratory system right behind the circulatory system because they work hand in hand in order to both be able to fully do their job. So your circulatory system is obviously going to circulate blood throughout your body, but it is using that blood as a vehicle to transport a variety of materials to all the cells that make you up. So we know oxygen right off the bat, that comes to everybody's mind. It's also going to transport glucose and other materials to your cells that they need in order to get energy. And then it's also going to pick up CO2 and waste product from your cells and get that cleaned out of your system so that you don't build it up within your body. So there's a lot going on with the cardiovascular system and how it ties into the respiratory system, getting that oxygen delivered and getting the CO2 removed. So we do pair up cardiovascular system and the respiratory system and put them back to back, just so we can talk about those ways in which they work together. So the first slide talks about the main functions that you have with the respiratory system. And for a lot of people, not going to be a huge surprise when we're talking about ventilation. So that is the process of taking air in as well as getting rid of it. External respiration as well as internal respiration. I know those are separated by one there, but when we talk about internal and external respiration, when you inhale and get air into your lungs, that is external respiration until the oxygen from that air that you took in actually diffuses over and makes its way into your bloodstream. It's not inside of you. So if that air is in your nasal passages, if it's in your trachea, if it's in the lungs themselves, that is still considered to be external. Once it actually makes the move over and it is part of your bloodstream and with your red blood cells, that is internal. Transportation of gas or transport of gas, I've talked about that already, just getting the oxygen delivered to the cells and then getting the CO2 collected and getting it out of your body. And then the process of cellular respiration. So cellular respiration was a conversation we had on early on in semester 1. So when we talk about getting oxygen into our body, it's not just getting it into the lungs, and we associate breathing with the lungs. So if we get the air there, that's where it stops. It's not about just getting that air into your lungs. We have to get it into your bloodstream because the blood is actually going to deliver it to your cells. And once it gets to the cells, that's where oxygen can really do its job. Oxygen is designed in a way that it is able to pull materials to it. And because of that factor, it can draw a lot of ions toward it. And that really allows it to build ATP molecules. And ATP is the fuel source for our body. So the oxygen molecule, we're not just concerned with getting that into our lungs. We have to get it over into the bloodstream so that the blood can deliver it to the cells. The cells are going to push it into the mitochondria. And the mitochondria are then going to use that oxygen as a way to manipulate, line up ions where they need them to be so that they can build lots of ATP molecules. If you move over to the second slide in your packet, it talks about the different parts of the respiratory system. It is divided into two parts. We have the upper respiratory system as well as the lower respiratory system, and it identifies the main structures that you would find in each. So your nose, your nasal cavity, as well as the sinuses and your pharynx are all going to be considered part of your upper respiratory system. Now, the pharynx itself is not an actual structure, it is a space. So where the nose and the mouth come together in the back, that is going to be the pharynx, but it's not a physical structure. The lower portion of the respiratory tract is going to be the larynx, the trachea, which a lot of people refer to as the windpipe. It also will involve the bronchial tree, which you'll see a picture of here in just a few minutes, and then the lungs themselves. So that is the division that you have between the two parts. If you flip over to the structures of the nose, so obviously we've taken a cross section of the head, kind of opened it up so that you can see the middle portion of your face. So working our way down the left-hand side first, looking at the frontal sinus. So a sinus is going to be a cavity that you have within a bone. And these cavities, number one, are going to help reduce bone weight. So we have them in places where we can get away without having solid bone. And just to make sure that our skeleton isn't any heavier than it has to be. Now, with the sinuses that we have within the skull structure, they're actually lined with a mucous membrane as well. And so they will produce mucus. Now, wherever you have a mucous membrane, you also have a way to drain off that mucus, and the mucus production matches the drain off. So you constantly have mucus there, but you're also constantly draining it off so that it doesn't cause any problems. In the case of a situation where somebody is sick, they will start overproducing that mucus and they can't drain it off as fast as they're producing it, and that's when you start getting the runny nose, the stuffy feeling in your head, because that mucus is now jam-packed in there and causing all sorts of symptoms that we associate with having a cold or being sick. The next one on the left-hand side, the nostrils, so that's going to be the opening into your nasal passages. And then we have the hard palate. So if you take your tongue and put it to the roof of your mouth, you'll notice that it's a firm structure. That is actually the division between your mouth and your nasal cavity, and you can see that from that cross section, how it does divide and separate those two. It does not go all the way to the back, so you do not have a clear-cut division between the nasal passages and the back of the throat, and that place where those two come together, that is that pharynx. So when you track that to the back, if you look at the nostril and go all the way to the back of the throat, and if you look at the mouth and follow that hard palate to the back, you'll notice that eventually they do meet and come together, and that is your pharynx. The uvula, that is a small structure that hangs down at the back of your throat. And a lot of people just kind of think it doesn't really do anything, but that uvula is attached to a skeletal muscle. And when you swallow, the job of that uvula is actually to swing up, and it closes off that opening into your nasal passages. And this is to ensure that when you swallow, or if you're drinking or if you're eating food, that material goes down and it's not allowed to come back up. And if you've ever had a situation where you did have something come out of your nose, somebody made you laugh at the wrong time, and all of a sudden you've got milk squirting out of your nose, because it is run by a skeletal muscle, it is easy to confuse. So if you start doing some other respiratory activity, such as laughing at the point where you're trying to swallow, that little muscle doesn't know what to do, and so instead of swinging up and closing off the nasal passages, it just kind of stays where it is, and it leaves that area open, and that's why material can come back up through your nose. Then we have the tongue. So the tongue is a strong muscle that we have in the body. It's used to push food around in our mouth, help to roll food into a ball, and help with the swallowing process. The next one that we have is the hyoid bone. The hyoid is unique in the fact that out of the 206 bones we have in the human body, it is the only one that is not attached to any of the other bones. It does not form a joint with any other. It actually serves as a point of attachment for the tongue. So what you can see in your mouth, your tongue is probably going to run another 3 to 4 inches down into your throat. And that hyoid bone is going to give a point of attachment for that muscle and the other structures that are needed to secure it in place. Just below that, we have the larynx. The larynx is also known as the voice box. And so this is, you'll notice right at the top of the trachea. If you put your hand to your throat, you can notice that cartilage that is going to make up that larynx or that voice box. And then the last one that we have on the left-hand side is the trachea itself. Now, I want you to take a look at the esophagus as well. So you have 2 tubes that run down the back of your throat. You have the trachea and you have the esophagus. If you've ever heard somebody refer to, somebody's choking and they say, oh, did it go down the wrong pipe? This is actually what they are referring to. Those two tubes that you have, the trachea is in front and the esophagus is posterior. It sits behind the trachea. Now, the trachea has cartilage around it to help hold it open. The esophagus does not have that. So when the esophagus is not in use, it almost closes down flat. But it does sit posterior or behind the trachea. So that arrangement is very important. We'll talk about that a little bit more later. If you move over to the right-hand side, it starts off with the nasal conchae, superior, middle, and inferior. Now, with these structures, this picture doesn't really do it justice, but these structures are actually rolled like scrolls. So it is going to fold over itself several times, and you don't at all get that from the way they have it designed in this picture. But what happens is anytime you take something and you roll it over, you're able to pack more into a small space. So by having that scroll-like shape, it increases the surface area of the nasal conchae, and we have two important things that are going to be attached to those nasal conchae. The first one is going to be a mucous membrane, and obviously with air coming in and out of the nasal passage, that mucus is going to help warm air. It's also going to help trap anything that is floating in the air that we don't want to go all the way down to our lungs. So those mucous membranes are very important to have in that area. You also have some of the receptors that are going to assist in your ability to smell. And so again, having that increased surface area, we're able to pack more of those receptors into that location. And it's a benefit, but even with that added benefit, we still, in the animal world, have a very, very poor sense of smell. The next one that you have there is the sphenoidal sinus. So this is another sinus, another cavity that we have within our bone structure. And I didn't mention it earlier, but the sinus is going to help also with your voice, the sound of your voice. So as air is moving in and out, it hits that hollow bone and it helps with the sound production that you produce and the actual tone of your voice. The vocal cords are also going to play a part in that. The thickness and the length of the vocal cords will help determine your voice as well. But the sinuses play a part in that, and that's why your voice sounds different when those sinuses are filled with mucus, because normally your sound production is bouncing off of a hollow bone area, but when that fills and clogs with mucus, now it's a deadened sound, and that's why you'll notice you sound different when you speak when you're sick. The next one that we have is the pharyngeal tonsil. And I'm actually going to pull out the three tonsils that we have here. So we have the pharyngeal tonsil. If you go down a couple, you'll notice the palatine tonsil, and then you have the lingual tonsils. So the tonsils are going to sit in this particular area of the body because they are glorified lymph nodes. So they are oversized lymph nodes, and the job of a lymph node is to hold on to any material that is not supposed to be in our body, and we don't want it floating around. And so we pack that into these tonsil areas until it can be dealt with and made sure that it's not going to do any harm to the body. So it would make sense that this is an area where we'd want more than just one, because you have a lot of material with the nasal opening, with the mouth opening, with the ears, just a lot of places for outside invaders to get in. And so we jam pack this area with a lot of tonsils just to deal with all of that material coming into our body. Just below that, we have the nasopharynx. And again, I'm going to pull out all three. You have the nasopharynx, and then if you drop down a couple, you'll notice the oropharynx. And then the last one, you have the laryngopharynx. So their names come from where they're positioned. Naso, that one is closest to the nose. The oropharynx is closest to the mouth. And then you have the laryngopharynx, which is closest to the larynx. So those are just referencing the three different locations within that area where the nose and the mouth come together. One other thing that I wanted to touch on was the opening of the auditory tube. And so this is going to lead to the ear. A lot of times we associate ear infections with little kids, and people just assume ear infections come from the outside in. There's an opening that goes from the mouth to the ear, and because of that, a lot of times ear infections start from coming in from the mouth, not from coming in through the ear. And if you think about little kids and why little kids tend to get ear infections more often, is because they are constantly picking stuff up and putting it to their mouth. And so it's just an easy way for that infection to get in initially, and then it just travels up that auditory tube into the ear and causes the infection. The other one that we haven't talked about yet is the epiglottis. So the epiglottis is going to be another small flap of skin, and its job is to cover either the trachea or the esophagus. So if you are taking in food or drink, that epiglottis will cover over the trachea just to make sure that food and other material doesn't get down into your windpipe. If you are taking in air, that epiglottis will fold over the esophagus to make sure that that air doesn't go down to your stomach. Now, again, this is a flap of tissue that is connected to a skeletal muscle. It's not hard to confuse it. So if you laugh or talk at the wrong time, that epiglottis doesn't know which one it's supposed to cover. And so it will just stand straight up. It won't cover either one of them. And that's when you get food down into your trachea and you start coughing and hacking trying to get that up. So if you move on to the next slide, it talks about the trachea specifically. And so what you are looking at with this picture is from the larynx down to the trachea, and then as it divides and moves into both of the lungs. So the trachea, as I already said, a lot of people like to refer to it as the windpipe as well, but it has some very unique features to it. Because the trachea sits on the front side of your throat, it needs to have some sort of structure and some sort of support to hold it open. Because every time you had any sort of pressure applied to your neck, if it didn't have that structure to help hold it open, it would be very easy to close it off. And then obviously getting air down into your lungs would be removed. So around the trachea itself, you'll notice it has a series of rings. Those are actually made of cartilage, and that is to make sure that it has structure and it can withstand resistance, so you don't have to worry about the slightest amount of pressure closing off your air supply, excuse me. So you do have a series of cartilage rings running up and down the trachea. Now, this particular picture doesn't do it justice, but if you were to look at the trachea top down, you would actually notice that it is shaped like a D. So it's round around the front, but when you get to the back side, it's straight. So it looks like somebody has made it into the letter D. The reason for that is even though it has those cartilage rings on the front side, they don't go all the way around. They only go around the front side, and the back side is cartilage free. And the reason for that is because of the earlier picture I showed you with the esophagus running right down behind the trachea. If the trachea had those cartilage rings running all the way around it, it would interfere with the esophagus and your ability to move food down your esophagus. So you needed to have a soft part of the trachea up against the soft part of the esophagus so that it had the ability to flex and allow that food to move down and not be up against a rigid structure. If it was right up against a rigid structure, it would be very difficult for you to get that food to move down your trachea the way everything is designed. So the cartilage rings just around the front side, they do not go around the back side of the trachea. Now, the trachea is going to eventually divide, and at the point that it divides and dives down into the lungs, it is no longer the trachea, it is now the bronchi. And so as soon as you have that division from one tube to two, you've changed the structure. So when it's one tube, it is the trachea. Once it becomes two, we're now into the bronchi. So if you move to the next slide, it talks about the bronchial tubes, and you do have two, and that would make sense. You have two lungs, and so when the trachea divides, one of those tubes is going to dive down into the lungs. One of those tubes is going to dive into the right lung. The other tube is going to dive into the left lung. And so that's why we have the split, making sure that each one of the lungs is going to get served with the air that's coming in through the trachea. Now, the structure of the lungs is slightly different. So the right lung is going to be larger, the left lung is going to be smaller, and that is to accommodate the heart. And because you have the size difference, the right lung will have 3 total lobes, and the left lung only has 2. And that will come up a little bit more um, as we get into the other slides. Now, with the trachea transitioning into the bronchi and then continuing to move down into the lungs, this is another thing that I have found, is that people have this image of the lungs as kind of being like balloons. It's open and filled with air inside the lungs, but it's just kind of a hollow space. And that's not the case with the lungs. The lungs are tissue all throughout. If you've ever had the opportunity to see an actual lung and cut into it, you will see these little holes, pockets. They kind of look like air bubbles within the lung tissue, and those are the actual bronchi or bronchioles that you are seeing when you cut that through that tissue. But those bronchioles are going to be all the ways that that air is going to continue to get down into all the parts of the lung. So it's a transportation system to get that lung, or to get that air all the way into the lung. So the next slide that you have talks about how the tubes branch. And this image that you have here, so you can see the trachea right in the middle, the large tube. You can see where the trachea branches and becomes 2 tubes. But what they've done with this picture, and I think it's pretty impressive, is they have removed the actual tissue of the lungs, and they have left behind the trachea, the bronchi, and the bronchioles. So that is what you're seeing. Now, we generally refer to this as the bronchial tree, because if you really look at this, if you were to take that picture and flip it over, you have the trunk, that would be the trachea. You have the large branches, those would be the bronchi. And then you have the smaller branches as you move out, which would be the bronchioles. So these tubes keep splitting, and every time they split, they get smaller in size, and they'll continue to split and split and split so that they get down, like I said, into every single part of the lungs. So it talks about the ways that the tubes are going to branch. We've already talked about the right and left primary bronchi. So one would go into the right lung, one goes into the left lung. From there, that starts to change a little bit. Because the right lung has 3 lobes to it, when you get into the secondary bronchi, now we start to get a different number of bronchi in each lung. So in your right lung, because there's 3 lobes, you are going to end up with 3 secondary bronchi. In the left lung, because there are only 2 lobes, you only end up with 2 secondary bronchi. So there's a little bit of a division. 1 trachea, 2 primaries, and then in the right lung, you're going to get 3 secondaries. In the left lung, you're just going to get 2. From there, when we get into the tertiaries, it changes a little bit again. You have more tertiaries in the right lung than you do in the left lung. I've seen actual numbers put to this, and I've seen the numbers vary. So in some places, it will say that you have 10 in the right lung and 8 in the left. But like I said, as we start to get deeper into the lungs, these branches just start to fray and get smaller and smaller to the point it becomes very, very difficult to count them. So the interlobular bronchioles, 12 to 14 generations, again, a little bit of a number difference because you're going to have more in the right lung than you would in the left lung. And when you get into the terminals and the respiratory bronchioles, now you're numbering in the thousands. So just a massive network of tubes that are running through the lungs to make sure that we are getting air to all parts of the lungs. The next slide that we have looks at the alveoli. So at the end of your bronchioles, so we have the trachea, divides into the primary bronchi. Those keep splitting down, and when they get small enough, they become bronchioles. And when you track those bronchioles all the way to their end, you are going to find these alveoli. Alveoli are tiny little air sacs. They look like clusters of grapes. But if you look at this picture, you'll notice that over each one of those clusters, you have a network of capillaries. This is where the actual site of gas exchange takes place. So what happens within your alveoli is that air comes in, passes through all of those tubes, down into the bronchioles, and at the end of the bronchioles, it gets into these air sacs, these alveoli. Now, the process, again, this is a first semester topic. We talked about diffusion. Material likes to go from an area of high concentration to an area of low concentration. So when you inhale that air, it's not 100% oxygen, but it has more oxygen in it than your blood supply. Remember, your blood has been circulating through your body, it's been delivering oxygen to all of your cells. So by the time that blood comes back to your lungs, to these alveoli, your blood is lower in oxygen. You've just inhaled this air from the outside, which is high in oxygen. The process of diffusion, things want to go from an area where it's high concentration to an area where it's low concentration. So a lot of air or a lot of oxygen in the alveoli, not so much in your blood vessels. What happens is that oxygen is going to diffuse from the alveoli into those capillaries and replenish the oxygen level in your blood. On the other side of that, your CO2, your blood, as it was circulating through your body, was collecting all of that CO2, all of that waste product from your cells. So now your blood is higher in carbon dioxide. When you inhale the air from outside, not a lot of carbon dioxide. So here we have just the opposite. We have a high level of carbon dioxide in your blood. We have a low amount in the alveoli. So diffusion is going to move the carbon dioxide from your blood across those alveoli walls back into the alveoli. And now when you exhale the next time, you're going to force that carbon dioxide out. So that's how the gas exchange happens. You get the air all the way down into those alveoli, a lot of oxygen, not a lot of CO2, and so those gases just exchange with each other. With the alveoli, they are tiny little air sacs. You are born with the number that you will have for your entire life. You are talking about hundreds of millions of alveoli that are going to be located in your lungs. The problem with the alveoli is that they are not replaceable. Once they are damaged and broken, you cannot fix them. They do not regenerate. And because of this, over your lifetime, if you don't expose yourself to a lot of harmful things, your alveoli, you'll have enough to last your entire lifetime. But if you are involved with things where you are going to break these alveoli at a higher rate, so if you are living in a highly polluted area, a lot of smog, if you are involved in activities, huffing chemicals and things like that into your lungs, smoking, obviously a huge one, you break those alveoli at a much higher rate. And over a period of time, if you start breaking too many of them, that exchange of gas can't happen, and now you have a problem. So when you hear emphysema, emphysema is an indication that they have broken so many of those alveoli that that gas exchange just can't happen at a high enough rate for them anymore. So the next slide that you have does kind of give you a visual to what I was talking about. Here, what they did is they took just one alveoli, so one of those little clusters. You can see the capillary running on the outside, and both the alveoli as well as the capillary have very, very thin walls to make the process of diffusion easier. So diffusion means that a material is going to move from one location to another location where it's highly concentrated to begin with into an area where it's in low concentration. So you inhale that oxygen, you get that oxygen down into the alveoli, and those gases will start to move across those capillary walls and those alveoli walls. The last slide that you have takes a look at the lungs. The lungs themselves are going to be given protection from your rib cage. And we talked about the fact that any of your bones that are rounded are going to offer some measure of protection. So the skull is rounded, protects the brain. The ribs are rounded, protects the heart and the lungs. Your hips are somewhat rounded to help protect your reproductive organs. So we see that structure of the rib cage surrounding both of the lungs to make sure that they are protected. The rib cage, excuse me, if you look at it, you'll notice that it has the cartilage up front. And that is because we need the rib cage to be able to expand and contract based on what our lungs are doing. So when we take in air, we need those lungs to expand, and the rib cage has to be able to give with that. And so those cartilage pieces that we have on the front of the rib cage are very, very important to do that, so we can go through the process of breathing. Now, the one thing that we don't see in this particular picture is the diaphragm muscle. So the diaphragm muscle runs immediately underneath the lungs, and it plays a very big role in the process of breathing. So a lot of people assume that they just pull air in and they push air out, and that is the actual act of breathing. And that's not the case at all. Wherever we are, we have a certain amount of atmospheric pressure that is pushing down on our body. The inside of our body has to push back with the same amount of pressure to keep things in balance. Whenever you have a situation where those two levels of pressure are not balanced, you're going to see one of two things happen. If the atmospheric pressure pushing down on our body is greater than what our body comes back with, we would implode. If the pressure inside of our body is pushing out more than the atmospheric pressure pushing in, we would explode. So when we talk about the process of breathing, what's actually happening is our body is regulating and maintaining that atmospheric pressure inside and outside of our body. So what happens is that diaphragm muscle runs right under those lungs. When it contracts, it pulls on the lungs and it causes the lung to open up. Well, when you have that increased amount of space, we have to balance out the atmospheric pressure. And so immediately air runs into the lung to balance the pressure levels. You are not pulling that air in whatsoever. It is just your body's way of trying to make sure that inside and outside, those two pressure levels are maintained. Then the diaphragm will relax. When it relaxes, the lung will collapse back down on itself, and that forces the air out. So the actual process of breathing, nothing that you are doing. It is just simply that muscle contracting and then creating a space for air to come in, and your body making sure that pressure inside, pressure outside is maintained. If you have the hiccups happen because that diaphragm muscle gets a spasm and it contracts much faster and quicker than it should. And because it contracts with a lot of force, it opens up that lung very quickly. The air has to rush in very quickly to get that balance maintained. And because that air rushes in so fast, you get the hiccup sound as a result of that. So that takes us through our respiratory chapter. We are going to, the next time we meet, just a reminder, we are going to have a test over the cardiovascular and the respiratory system. Make sure that you check Blackboard for your study guide. And if you have any questions, let me know.